Hello everyone, this presentation is titled The Smart Irrigation System, prepared by Utsav Patel, Pipalya Jil, and Javel Savani. Today, we will explore how to build an automated watering system using Tinkercad. This project enhances water efficiency and smart gardening techniques for home and commercial use both. Problem state the need for efficient irrigation. First, water wastage in traditional irrigation. Second, efficient crop watering leads to losses. Third, rising water scarcity issues globally. Fourth, demand for sustainable farming practices. Introduction to smart irrigation and Tinkercad. First of all, smart irrigation. It is a technology that automates plant watering based on soil needs. Tinkercad platform. It is the online tool for simulating electronics and code virtuality. Benefits. By using this tool, we can reduce water waste and support sustainable agriculture. Overview. Innovative solution for water efficient farming. Combines digital electronics with environmental sensing. Enhance crop field and resource management. Project goal. Automated plant watering. First, detect soil moisture and sunlight. Sensor monitor moisture level in real time. Trigger water pump. It triggers water pump when activate pump when soil is dry to irrigate plants. Save water. Only water when needed, avoiding wastage of water. System components and circuit design. First of all, hardware components. Arduino microcontroller, solid moisture sensor. It is used to measure soil moisture. Temperature sensor, used to measure temperature. Light sensor, relay module, and water pump. Then after circuit connection, sensor connects to Arduino analog pins. Relay control the water pump power supply.
Microcontroller implementation, Arduino code and logic, data acquisition, continuous sensor reading, decision making, logic to activate irrigation, communication, feedback to monitoring system. The sensor selection explaining the reason behind choosing a specific sensors. Soil moisture sensor critical for determining when the plant need water, prevent both underwatering and overwatering temperature sensor. Help factor in weather condition. High temperature may require more frequent watering. Sunlight sensor. Motoring ambient light, which indicate affect water needs to due to photosynthesis and evaporation rates. Here we are going talking to about sensors. Here we select sensor. Soil moisture sensor, temperature, sunlight, soil moisture. It detects water content, prevent to overwatering, and temperature sensor measure ambient heat affecting irrigation needs. Sunlight monitors sunlight and measure ambient heating affecting irrigation needs. Here we are talking about Tinkercad code, sensor and control logic. Read sensor data. Periodically check soil moisture and temperature value from sensor. At the beginning, he check a value from soil moisture sensor and temperature sensor. Then compare threshold. Determine if the soil is dry and temperature is more based on predefined threshold. It checks a condition like if a soil is dry and temperature is greater than 30 degree, then it going on to start pump, water pump, control water pump, turn on and off accordingly irrigation need. Here is circuit diagram. So we are going, it takes, this is motion sensor, it takes input and going to that input in Arduino, and same as temperature motion sensor and light motion sensor, and it will display on the, you can see LED LCD 16 cross 2, and if condition was correct, then it will play a motor. And this is link to open Tinkercad project to run that. Here we are going to describe an circuit. First of all, we start simulation. It takes time. So we are going to describe everything. Start from here. This is motor driver, HD, temperature sensor, at light sensor. It is temperature sensor. It is Arduino. This is LCD 16 cos 2, soil moisture sensor, and DC motor. First of all, here taking a temperature as minus 40 degree and light is 0, 2, and moisture is going to 0. Then motor will work. If we are going to increase the light, then we are going to increase temperature, then and moisture will 0, then it will work. But if moisture will increase, then after that it will stop. And if we are going to decrease in temperature and also decrease a moisture sensor, then it will run, as you can see. So here we have condition like temperature is less than 30 degree or light is less than 2, and temperature is temperature is less than, light is less than 2, and moisturize is less than 2. If we are putting is or and here and, so if any of two is completed and moisture is less than 2, then it will work. Here we are going to discuss code. Let's hear the predefined library definition, initialization with pin, enable pin, input pin, and input pin 2 for motor driver, and temperature pin, light pin, and moisture pin connected to A1, A2, and A0. When void setup, LCD begin start. When LCD begin means it will when it is start. Set motor control pins as output. It gives an output pin to pin. Void loop. Int temperature value and it reads data from a temperature pin and analog grid. It takes as well as light value and moisture value from same different sensor. Convert the sensor value to their corresponding unit. Here it is int temperature and it is specific value from each sensor. Float temperature, float so temperature value star 5 it means multiply by 5 and divide by 1024 minus 0.5 into 10. It will be is protected. Serial print temperature. Serial print temperature, it will print on a serial, and LCD clear, same as this above, it will print on LCD screen everything. If here is given the condition, if temperature is greater than 30 or light is greater than 2, then moisture sensor is and less moisture sensor is less than 4, then it will check condition, else if the condition is right, then motor is turned on. It going to in one as high. Otherwise, they turn off the motor. And this same condition is going to repeat after every 1 second. Here, here is the simulation and testing on Tinkercad. Test moisture response. Simulate very soil moisture level in virtual environment. Verify pump activation. Confirm pump triggered only when soil is dry. Debug and optimize. Adjust threshold and code based on a simulation feedback.
Irrigation control. Once the system detects that the soil is dry, it initiates the next crucial stage, activating the irrigation valves. These valves control the water flow to plant bed. We have implemented logic to ensure the system doesn't flood the soil. Instead, it uses time-based or sensor-based shutoffs. For example, once the soil moisture reaches a healthy level, the valve closes automatically. The valve system is directly connected to the relay model, which is in turn controlled by the Arduino. The Arduino monitors both moisture and time to determine when to stop irrigation. This logic helps ensure precision, it saves water and protect the plant from root damage caused by excess water. By automating this entire cycle from detection to water flow management, we eliminate the need for manual oversight, making the system ideal for remote or large-scale operation. Power management. Energy efficiency is another key feature of our system to make it sustainable. We incorporated solar panel as the primary energy source. During low light conditions, battery storage kick in to keep the system running. Additionally, we use low power sensor and program microcontroller to enter sleep mode when inactive. These help extend battery life and make the system more eco-friendly. Results and potential improvements. Our test showed very promising results. The soil moisture sensor delivered accurate and consistent reading, which helped the system irrigate precisely when needed. This led to a noticeable reduction in water usage and proving the system effectiveness. For future upgrades, we plan to integrate weather forecasting and IoT connectivity. This will allow remote monitoring and smart control using real-time environmental data. Real-world application. This smart irrigation system has broad practical uses in home garden. It can reduce the need for daily maintenance while ensuring plants are healthy. In greenhouse, consistent watering is key. Our system can provide that without human intervention for farmers in remote or arid regions. This could be a game changer, especially if linked to solar power, making it completely self-sufficient, and additionally, the project has educational value. It is a great example for student learning about embedded system, automation, and environmental tech. School and colleges can use it to demonstrate real-world problem solving using basic electronics and coding. Conclusion or benefit future enhancement and impact. To conclude, our smart irrigation system, it offers multiple benefits like it conserves water, boosts plant health, and supports sustainable farming. While looking forward, we aim to add AI capabilities and expand sensor support to cover more environmental factors. Overall, this project demonstrates how technology can directly support global efforts towards sustainable agriculture. Thank you.